Hello, this is Miriam Qasim, and this is my Lab 5 projectile motion. Here's the index. We'll be having an introduction and explanation of the physics principles, the experiment code, the comparison between the theoretical and experimental models, and lastly, the discussion. For our introduction, the purpose was to track and analyze the motion and position of a ping pong ball thrown at an angle using tracker. Our aim was to have the experimental model created using tracker as accurate and precise to the theoretical model created using GlowScript. As for the main results, the difference in the horizontal displacement was 0.064 meters and 0.394 meters for the vertical displacement, and that was the difference between tracker and GlowScript. We have two main physics principles, Newton's first and second law. Newton's first law states that an object in motion or at rest will stay in motion or at rest unless acted upon by an external force. And Newton's second law, more commonly known as F is equal to ma, can be rearranged to obtain the velocity update formula and the position update formula. Here's the experiment. The equipment was only the ping pong ball. Our systems and surrounding was ping pong ball and the earth for the system and the air for the surrounding. Here's the graph we obtained from tracker for the displacement in the vertical and horizontal axes. And here's our GlowScript code. At the beginning, we have the initial conditions obtained from tracker, ball position, and velocity. And then we changed the while loop to have the time set as 0.7667 because that was the duration of the ping pong ball falling. And then we have F net, which represents negative mg. We're also ignoring air resistance. That's why the gravitational force is the only force acting. And then we have the velocity and position update formulas. At the very end, we have the code for plotting the graphs for both the x displacement and the y displacement. Here is the GlowScript graph. We can immediately see for our x position versus time, the slope was constant, and therefore the velocity was constant. As for the y, the slope is decreasing, which shows that our velocity is decreasing. On the top right is the GlowScript tracker. As for the comparison between the experimental and theoretical model, we've obtained very similar looking graphs. However, our final displacements did differ slightly. For tracker, the x displacement was negative 1.546 meters. As for GlowScript, is negative 1.61 meters. For the y-axis, it was negative 0.826 meters for tracker and negative 1.22 meters for GlowScript. That difference could be obviously because of air resistance. We did, after all, ignore it, but it could also be because of multiple other reasons, and that brings us to the next section. Here are the sources of error. First, we have inaccurate initial velocity calculated. We could have inaccurately used the tracker information. After all, we only took the very first 2 points to calculate it. Second of all, we could have calibrated the video incorrectly because I didn't have a meter ruler at hand. Thirdly, we used a white background, so the tracking could be inaccurate. So, what if air resistance had a bigger effect? That would mean that the difference between the final displacements between tracker and GlowScript would be larger if we continue to ignore air resistance in GlowScript, obviously. And what does it mean? Since air resistance is negligible, did the x component of velocity stay constant? Why is that the case? The slope for the x position over time graph on tracker stayed fairly constant, and since the slope is equal to the change in displacement over time, which is obviously equal to velocity, the x component of velocity stayed constant. Why is that the case? Well, Newton's second law states that F is equal to ma, and since F net's x component is equal to 0, the acceleration in the x direction is also 0, meaning that the velocity in the x direction will stay the same. That is all. Thank you.